questions? Drake, did you say you had something?
Yeah. One on like 13, just for like terms of understanding of how you get sine by itself. I like barring mentioning the other sine of the problems like cosine, tan A, and cosine alpha. You get that to sine by turning tan into sine over cosine, and then just you take the two of them and then like put them down by greatest common or least common factor.
Right?
Okay.
You're just talking about that middle piece is what you're talking about?
Yeah. And for number 8, I just don't understand how.
And then you say, now we're talking about 8?
Yeah.
Okay.
That's just all I have.
Okay.
So how do you get the?
That's what I'm due first. Tangent pi over 2 minus x is cotangent. That's just an identity.
Okay, so you only want them in their simpler forms too?
So this can go further. I would think about this now as 2 separate fractions. Think about it as the numerator over 1 times the 1 over the denominator. The reason I'm going to do that is because cotangent I can write as cosecant x over cosecant x. So those can cancel. So we just have 1 over secant, which is cosine. Is that okay, Drake? Okay. Follow up to either of these two before we move forward. Okay, Natalie.
Just clarification, there's no one strict way to do these, correct?
Correct. Yeah.
Okay.
Yeah. There's often like an easiest way to do these.
Yeah, because I did a completely different little process. I still got cosine x.
Okay, so probably fine. Could be that it was wrong, like you did some illegal stuff and then just lucked into the right answer. That's possible. I just don't want to say like for sure you've done it right just because you ended up with the same thing. But likely it could be fine. Eddie.
How do you change cosine over 1 to CSC over SEC?
So if you just look at the identities, that's one of the things that you could make cotangent equal to.
Oh, it's cotangent.
Yep.
Yeah, my bad. I just thought.
That's okay. No problem. No problem. Paul.
Can you do number 2?
Sure. All right. So what I'm going to do is I'm going to start with an identity. And ideally, I want an identity that involves cosecant or sine, right? Because I know this is true, as well as cotangent or tangent, because I know that's also true, right? Just from reciprocals, I know those things, right? So if I go and I look at my identities, I'm probably going to use a Pythagorean because I have the piece that's telling me after I take the square root whether I'd want to use a plus or minus. So if I look at my identities, I see that secant is related to, cosecant squared is equal to 1 plus tangent squared, or cotangent squared. So that's what I'm going to use. So I have 1 plus cotangent squared, these are alphas, equals cosecant squared. Cool. Negative 3 squared is 9. I subtract 1 from both sides. I have cotangent squared is equal to 8. Square root both sides. Cotangent is plus or minus. The square root of 8 simplifies to 2 root 2. And since I know cotangent is positive, I can drop the plus or minus and just make that positive. Now what I'm going to do is I'm going to look for something that relates cotangent or tangent with secant and cosecant. So there I can say that cotangent is equal to cosine over sine. Cool with that? Hi, sorry, that's not the version I wanted. I wanted to say cosecant over secant. Is that okay so far, Paul?
Yeah.
And now I'm just going to solve this for secant. So multiply both sides by secant, and then divide both sides by cotangent. And now I can plug in my values for cosecant that I know. So -3. And my value for cotangent, 2√2. And if I rationalize my denominator, I end up with -3√2 over 4.
Okay.
So typically on these ones, I'm going to use a Pythagorean to start, because the inequality is going to tell me whether I want the plus or minus, and then probably a quotient identity to finish things off. That'll get 2 of the things that I know related to the third thing that I'm looking for. That's typically going to be the pattern. Mia, I saw your hand.
No, I'm good.
You're good? Okay. Lexi. Sure. Hi.
Hi.
Thank you. Eric Gomez. Pour vous. That's for you in French. Okay. So we look at 14. First thing we want to do is check for anything algebraic to do. Nothing to do algebraic, like factoring wise or combining with like term wise. So we're just kind of stuck trying to make a common denominator because we have 2 fractions that are added together. That's the only algebraic thing we can do. Is that okay? So if I look at 1 minus x and 1 plus x, the common denominator between those two would be it's going to be 1 minus sine y times 1 plus sine y. That would be the least common denominator. Since they're both relatively prime, there's nothing that divides both of them evenly. So the first one we'll just multiply by 1 plus sine y over 1 plus sine y, and the other one 1 minus sine y over 1 minus sine y. So when multiply it by 1, and multiply it by 1, so far so good? Now, if I look for algebraic things to do again, there's a whole mess of stuff to do now. Right? I have a positive sign plus a negative sign. That just cancels out and gives me 0. I have 1 plus 1 is 2. And then at this point, I'm sure that I'm going to want to multiply the denominators out. Since the numerator just has a 2 in it, there's going to be nothing to reduce with the denominator. So let's multiply it out and see if there's an identity that we could apply. So you could FOIL that out, or you could observe that this is really a difference of 2 squares. I have like an a plus b times an a minus b. So I know that it's going to multiply out to give me like a squared minus b squared, or 1 minus sine squared. Okay there? Now the only piece of simplification I could possibly do at this point is in the denominator, where I have 2 things in there. There might be a way using some identities to combine them and make one thing. So that's what I'm going to look for. When I see addition or subtraction kind of and things squared, I'm going to be looking at the Pythagoreans. Identities are typically the ones that are going to be useful to us. So I see I have a 1 down here, and I know that sine squared plus cosine squared is equal to 1. So I can replace that 1 with sine squared plus cosine squared. Now the denominator still has that minus sine squared, and the numerator still has a 2. But that's great because the positive and negative combine to give us 0. So we're left with 2 over cosine squared. Now I'm going to write this as 2 times 1 over cosine squared, right? And the reason I'm going to do that is just so it's easy to see the reciprocal identity that I'm about to apply. So 1 over cosine squared is just going to be secant squared, and the 2 just kind of comes along for the ride. And that's kind of as good as we could do there. So the trick was just making sure we made a common denominator to start, and you did the right common denominator. And then from there, everything kind of flowed reasonably naturally. But that would have been the roadblock. If you didn't do that correctly, then not a lot of hope. Eddie.
I have a different question.
I think we're good for that. Lexi, you good?
Yeah.
Okay.
So number 9.
Yeah. I'm going to do the exact same trick I did here in number 9. So I'm just going to rewrite that as sine squared plus cosine squared. Then I still have the minus cosine squared over sine squared. Those things add to give me 0. And then this just reduces sine x. Cool? So that trick where we replace 1 with sine squared plus cosine squared is useful, right? Like that's a trick you can use a lot. Amy. Sure. So 15, the first thing I want to do is to get the x by itself. So that just means I'm going to be doing the sine inverse to both sides. To do the sine inverse of root 3 over 2, I'm just going to go to the unit circle and look up where the y coordinate is root 3 over 2. That happens at pi over 3 and 2 pi over 3. So that's my answer for part A, because the unit circle just goes from 0 to 2 pi. Those are the only 2 places where we have that y coordinate. For part B, where we're solving over all real numbers, basically all I need is everything that's coterminal to pi over 3, and everything that's coterminal to 2 pi over 3. So that's all we have to do to write that. For part C, we're looking for everything between negative 2 pi and positive 2 pi. Well, we already have everything in between 0 and 2 pi from part A, right? So now all I have to do is worry about the things from negative 2 pi to 0. So all I'm going to do is find the things that are coterminal to pi over 3 and 2 pi over 3 that are inside negative 2 pi to 0. So I'm just going to subtract 2 pi from each of those. So that's negative 5 pi over 3 and then negative 4 pi over 3. And then part D, so we've covered negative pi to 2 pi in part C, right? That's a subinterval. So I'm just going to look from my answers from part C. So these guys are too small. Those are less than 1 pi, so I don't need those. And then I'm just going to worry about the stuff from 2 pi to 4 pi. So again, those are just going to be coterminal to pi over 3 and 2 pi over 3. So I'm just going to add 2 pi to both of those. So that's going to give 7 pi over 3 and 8 pi over 3. And that's 15. Was it too fast?
No.
No? Okay. I felt like I got going there. Sorry. Sometimes you just get excited. Having one of those math days where it's like, yeah. Only me? Okay. I feel bad then. That's okay. All right. Anybody else? Okay. You guys ready to do it?
Let's get it over with.